Just a reminder before we start the notes to read the section on these notes before going over the notes, as the notes are just a summary. Hi everybody, Mr. K here. We're starting section 2.2 called Electron Configuration. And this should take 2 days to cover. Before we talk about electron configuration, we need to talk about the electromagnetic spectrum first. All types of light, visible and other, travel at the same speed but have different wavelengths. The wavelength is measured in meters or nanometers. Here's a diagram of a wavelength or of a wave. The wavelength is measured from crest to crest or from trough to trough, and it's given the symbol lambda. The frequency of light, which is how many waves pass by a point in 1 second, is given the unit hertz, which is the same thing as per seconds. The wavelength and frequency are related by this equation, where c is the speed of light. Light, in science, is a mixture of all kinds of waves with different wavelengths, or colors. Prisms are used to separate the different visible colors when a mixture of white light is passed through it. So prisms are used to separate white light, which is a mixture of all visible light, into its various colors. And atoms can emit lights of various wavelengths, both visible and non-visible. We'll mention how they do this a little bit later on. So here's the electromagnetic spectrum. And you can see that the visible range makes up a very, very small part of it. To one side we have infrared, microwaves, and radio waves, and to the other side we have ultraviolet, X-rays, and gamma rays. Note that we're pretty familiar with infrared and ultraviolet. Infrared is just to the right of red on the visible spectrum. As we go to the left and reach violet, ultraviolet's just another side of violet in the visible spectrum. Notice that as the wavelengths get bigger to the right, their frequencies go down. And as the wavelengths go down to the left, the frequencies get higher. So when electromagnetic radiation of all wavelengths, both visible and non-visible, are passed through a collection of atoms of just one type or of one element, some of the wavelengths of light are absorbed by the atom, or maybe better to say, the electrons of the atom, causing the atom to become excited or have a higher energy state. So before they receive this energy, they're at a ground state, and when they receive this energy, they absorb some of those wavelengths and they're now excited. For example, here we have a source of many different kinds of light. In this case, we're just going to be talking about visible light. That's because that's what we can see with the human eye. It goes through this sample. Again, the sample is one type of atom. And then if we filter out the light into its different arrays of colors from red to violet, we can see that there are some lines missing. These lines correspond to a certain wavelength or frequency that were absorbed by this sample. And similarly, when an excited atom, that is one that has energy, loses that energy, it emits those very same wavelengths. So here we have an excited sample of the same material, and it's emitting light. We go ahead and break up the light into its various parts, and we can see the light that it's emitting are the same 5 wavelengths that were absorbed by the sample. Remember that the Bohr model says electrons orbit the nucleus. If an electron absorbs energy, it can jump from one orbit to another using the energy that it absorbed to make that jump to a higher energy state. And again, this is called the excited state. This state, however, is unstable, and at some point the electron will fall back down to its original energy state, releasing that same energy that was absorbed. So let's go back a slide. That's why the wavelengths that are absorbed by the sample are the same ones that are emitted. The energy absorbed or released by the atom is called a photon. A photon is a packet of energy. The higher the frequency, the higher the energy of the photon. So here you can see we have the excited state up here and the ground state here. This one on the right shows when an atom receives energy, this certain wavelength or frequency of energy. It jumps up, and when it comes down from the excited state back to a ground state, it releases the same photon of energy. This change in energy is equal to the energy of the photon. There's an equation for the energy of a photon using Planck's equation. So the energy of the photon is equal to this constant, Planck's constant, times the frequency of the light that is absorbed by the electron. Using substitution, we can change this equation to say, well, the change in energy of the electron is equal to Planck's constant times the frequency of the light. The fact that energy can only occur in bundles or steps, as opposed to being continuous, gives evidence that electrons can only inhabit certain energy levels, or shells, or orbits, and they can't be located any distance away from the nucleus. And this is evidence for the Bohr model being correct, that there are these discrete orbits that the electron can be in, but it cannot be in between orbits. It has to be inside one orbit. Hydrogen, like all elements, gives off energy, or light, when an electron falls from a higher energy state to a lower one. Some of these wavelengths are visible light, that is when the electron falls down to the second energy level. Some of these wavelengths are ultraviolet light, when an electron falls down to the first energy level. And some of these wavelengths are infrared light, when the electron falls down to a third or higher energy level. So the atom gives off light when the electron falls from a higher energy state to a lower one. And here's a diagram representing what was just said on the other slide. When you go from a higher energy state down to the third level, it's infrared. When you go from a higher energy state to the first level, it's ultraviolet. When you go from a higher energy state to the second level, it's, depending on which energy state you started at, it's a different visible color. Now it's possible when an electron or atom absorbs energy, the electron is completely removed from the atom, and we could say that it goes to an infinite energy shell or level. When that happens, it's said to be ionized, and the energy required to remove this electron from its ground state in a mole of gaseous atoms, ions, or molecules is called the ionization energy. So we can remove electrons from atoms, we can remove electrons from molecules, or we can remove electrons from ions. Something can already be an ion, and we remove an extra electron from it. Whenever we remove that electron, that is the ionization energy. The energy required to remove that electron is the ionization energy. Sometimes light acts like waves. When light passes through a small slit, it diffracts or spreads out, but sometimes light acts like a particle. For example, the light energy absorbed by electrons is done so in discrete amounts, or packets. And the same is true for electrons. Sometimes we can explain electrons as particles, and sometimes we can explain them as waves. When we explain them as waves, we have to use quantum theory. Schrodinger's model of hydrogen states that a wave equation can be used to describe the behavior of an electron, just like they are used to describe how light acts. His equation can be applied to multi-electron systems, and its solutions are known as atomic orbitals. This is in contrast to Bohr's model, which was only valid for the hydrogen atom, which had just one electron. But his model, Schrodinger's model, is applicable to multi-electron systems, or any atom. The orbital is a region around the nucleus in which there is a 90% probability of finding the electron. So as we said in the previous slide, although we can't know the electron's exact location, we can have a picture of the probability of finding it at any given location. Schrodinger's model says that that location where it might be is called an orbital, but because an electron technically can exist anywhere, we say the orbital size is 90% probability of finding the electron in there. And that can be seen here. Technically, an electron can exist any distance away from the nucleus, but anywhere within this boundary there's a 90% chance of finding the electron inside here, and only a 10% chance of finding it outside. So we say the orbital, the size of the orbital is such that The electron spends 90% of its time inside the boundary of the orbital. Now we're going to do a question for the hydrogen atom, and we're also going to do a question similar to number 14 from page 75 of your book. The first question we're going to look at says, for a hydrogen atom, a missing line in the absorption spectrum shows up when an electron moves from which levels to which other levels. State all possible correct answers. First thing we have to ask ourselves is absorption versus emission. Is the atom gaining energy or is it losing energy? And when it's absorption, it's gaining energy. So it's going from a lower energy state to a higher energy state. The second part of the question says visible. Visible has to deal with this energy level right here too. The visible lights happen when they're emitted when we drop down to the second energy level or when we move up from the second energy level. So the visible light being absorbed happens when an electron goes from the second level to the third level, the second level to the fourth level, the second level to the fifth level, or the second level, well, it's not stated here, or the second level to the sixth level, which isn't listed on here, so we don't have to answer that one. I also want to do number 14 from your book. It's on page 75. There's not anything to write down, so I'm not going to be writing with this one. It asks us to identify which of the following provides evidence to support the Bohr model of the hydrogen atom. So you have to know what the Bohr model of the hydrogen atom is. The first one says the energy of the lines in the emission spectrum of atomic hydrogen, and that one's true. The second one says the energy of the missing lines in the absorption spectrum of helium, as seen from the sun. That one's not true. It deals with helium and not hydrogen, therefore it doesn't have anything to do with the question. And the last one says the relative intensity of the different spectral lines in the emission spectrum of hydrogen. The intensities have nothing to do with the model of the hydrogen atom. The intensities would be different depending on how much of it you have, but it doesn't tell us anything about the model or the way the atom is set up. Electrons occupy spaces around the nucleus within orbitals, and each orbital can hold up to 2 electrons. There are various shapes of orbitals depending on what the sublevel is that the orbital is in. The s sublevel contains 1 orbital and is spherical. The p sublevel contains 3 orbitals and is peanut-shaped, or as your book says, dumbbell-shaped. There's a d sublevel which contains 5 orbitals, and each one has the shape of a double peanut, except for one of them. And the f sublevel contains 7 orbitals. Each energy level has an increasing number of sublevels. So the first energy level has just a s sublevel. The second energy level has an s sublevel and a p sublevel. The third energy has an s and p sublevel, but also a d sublevel. The fourth energy level has an s, p, and d sublevel, but also an f sublevel. And there are more sublevels at higher energy levels, but based on the number of elements we currently have in our periodic table, those sublevels don't get used, but they do exist. The s sublevel is spherical. So how is the 1s sublevel and 2s sublevel different? Well, simply the 2s sublevel is bigger. Here we have the nucleus of an atom. The 1s sublevel is indicated by the yellow sphere, and the 2s sublevel is indicated by the purple sphere. The p sublevel has 3 different orbitals, all oriented at 90 degrees from each other. Their names are based on their energy level and which axis they lie on. So the second energy level has a p sublevel, and it has 3 orbitals. So the 3 orbitals will be named 2px, 2py, and 2pz. 2px would be this one here, which is oriented along the x-axis. 2py would be this one. Y-axis goes in and out, and the z-axis goes up and down. So this orbital would be the 2pz orbital. And of course, the third energy level has the same thing. The third energy level has a 3px, a 3py, and a 3pz, which lie along these same axes, but are just bigger than the 2p orbitals.